Dear 10th class students, we are going to learn a few topics in physics now. You are aware that you have got a few topics in optics and a couple of topics you have in electricity and electromagnetism also. We shall begin our work with electricity. We are going to have an electric circuit system here, and we learn how to verify the Ohm's law. Now I am going to take a wire which has got electrons. Of course, you have to imagine that there are electrons here, and we take a battery which is a source of energy here, and we take a switch which is essential in the circuit, and I take another piece of wire to complete the circuit, and once we complete this circuit and we switch on, the flow of electric current begins to take place, and let us see what is going to happen. When I switch on here, you can find a short circuit because we are connecting the positive and negative terminals directly. There is no load here, so you are not supposed to do this. So we switch on here, and the energy of the electrons, which are moving very rapidly, and that energy must be consumed by an electric device here. So what I do now is I just split the junction here, and I want to incorporate a bulb. So I just take a bulb and keep it here in the circuit, and now I close the circuit and switch on again. Now the bulb glows. So it is essential for you to think of a device which consumes the energy, or rather you can say it resists the flow of electrons and converts the energy of the electrons into some other form. So now I have a provision here to change the voltage, and what I am doing now is I am trying to increase the voltage, as a result of which you can easily find the bulb is glowing brighter. So more voltage eventually means more current. Voltage here, by voltage I mean the potential difference. When I increase the potential difference across the ends, you can find there is a huge surge in the flow of electric current. The magnitude of current is increasing. So what I want to do now is I want to measure the voltage across the load. I take an voltmeter here, and I connect the voltmeter in parallel to the circuit, and let us measure the potential difference here. So you can find out the potential difference is 35.875 volts. So you should understand here, when you take an voltmeter, it measures the potential difference, and it should be connected in parallel in the circuit. You can't think of disturbing the circuit. For a while, understand, even if this voltmeter is not working, there is no disturbance to the flow of electric current. So anyway, we have the voltmeter now. We also have to measure the magnitude of current to verify the Ohm's law. So what I want to do now is I just switch off here. I split the junction, and I want to think of incorporating an ammeter which measures the current. Here I take the ammeter, and this ammeter, you should remember, it's always connected in series. So now we have the ammeter, we have the voltmeter connected here in parallel. Only thing now is we just switch on. The bulb glows, and you also can read the ammeter here. So what we understand here is when 35.9 is the voltage here, we are observing that the current here is 3.59 amps. So you can understand that V divided by I here is about 10. That is called resistance, and Ohm's law tells us that when voltage increases, the current also increases. So that is the point we have to verify now. So let me increase the voltage. When I increase the voltage, what you are finding is the voltage has increased and also the current has increased. And if you want to manifest this one, how exactly it's going to be observed, you can find the electrons moving very rapidly which indicates that the flow of current has increased. So this is how we find that the voltage across a load here is directly proportional to the current in the circuit, and that's how we verify the Ohm's law. Once again, let me reduce the voltage and show you that any decrease in voltage means decrease in the current. So I can reduce the current here. You can find now the electrons are moving very slowly. So this is how we verify the Ohm's law. Courtesy, this simulation is taken from Colorado University. Children, now we are going to discuss a few important ideas of electromagnetism. As you are all aware that when you have a magnet here, you can find the magnetic field around it. So if you want to know the polarity, check the polarity of this magnet, you can have a compass which is brought closer to that, and you can understand that this is the south pole of the magnet and this one is the north pole of the compass, because unlike poles they attract. You can also move this compass to a different place, to the other pole, and observe that this is the magnet's north pole and you have the south pole of the compass here. And what you can do here is that if you want to measure the magnetic field induction, the strength of a magnet, you can use a field meter, and this field meter you can move and find out the magnetic field induction. So if you take it near the poles, what you understand is that the magnetic field induction is considerably large, and even at this pole also you find the same. When you move slightly inside the magnet, it is still larger, and that you can find at the south pole also. But as I move out, what happens here is the magnetic field induction becomes weak. And not only that, when you move to the sides, the magnetic field induction is negligible. So what you should remember here is the magnetic field induction is maximum at the poles, and it decreases as you move away from the magnet. And not only that, when you come to the sides, so the lateral magnetism it's not that significant here. So now the question obviously is, why is the magnetic field induction more at the poles? So what you have to understand here is there are lines of force. When you have a magnet here, lines of force start from the north pole, you are aware of that, and they end at the south pole. So what is a line of force? It is the direction in which a freely moving north pole tends to move. If a north pole is allowed to move freely, it starts at this north pole, repelled by that, and it eventually moves towards the south pole. So if you can mark all those directions, that gives you the fields, like direction of those, the field at that particular point. So all these lines of force, they start from the north pole and end at the south pole, and this you find outside a magnet. And when you go to higher classes, you understand that these lines of force start from south pole and they move towards north pole inside the magnet, because they are all closed loops actually. Okay, fine. So I can move the magnet here, I can find out how the field is changing at different locations, because the field is associated with the magnet we are talking about. Okay, then I take a coil, I call this a pickup coil. This coil is, you have a conducting medium here, a wire in which you can see the electrons, okay, representation of the electrons. You also have a bulb connected to that, okay, conducting medium. So now what you should understand is that there is no power source. We are not supplying energy to this bulb to glow. But what I can do is I can move this magnet and make sure that there is an EMF produced there. Okay, so only when I move the magnet, the current is produced. It's not when I stop it. So the current is induced in the coil in two cases: when I move away the magnet or when I get closer to the magnet. Let us understand how this works actually. Like when I have the magnet here, there is a magnetic flux. Magnetic flux is, it's roughly the number of lines that pass through a unit area of cross section. So the number of lines which start from this north pole are more. As they move away, what happens here is that they just get dispersed. So magnetic flux is always the maximum at the poles, and when this magnet is coming towards the coil, what you understand is there is less flux here now, and when the magnet comes closer to that, the flux has increased. So eventually you can say there is an increase in the flux, or in general you can say there is a change in the flux. So when I move the magnet towards it, the flux has increased, and when I take it away, the flux has decreased actually. Now it's more near the coil, magnetic flux, because the magnetic pole is close to the coil. As I move away, the magnetic flux becomes less, and therefore in both the cases, when the magnet is approaching the coil or when the magnet is moving away from the coil, in both the cases you can find there is a change in the flux. That change in the flux is responsible for that induced EMF. So there is a current produced. So that current is making the bulb glow. You can see the bulb glowing only when I move the magnet inside the coil. So it's a relative motion. I can even think of moving the coil also, like you can start, it's only relative motion. What is important here is that the flux should change. Either you can move the magnet and produce EMF. Also there is a case where you can move the coil keeping the magnet stationary. So in both cases you can find out that EMF is induced. Okay, so if you don't want to see this bulb glow, you can also detect the current produced in the coil by having a galvanometer like. So you can find whenever current is passing in this coil, you can find the deflection in the galvanometer. What you can find out is the motion of the indicator there, the needle in the galvanometer is in the opposite direction when I go that side towards the coil, when I move away from that. So you can find the deflection. Rather it may be difficult for you because it's moving too rapidly. Okay, so you can understand now that whenever there is a change of flux due to the motion of the magnet, the current is induced in the coil. This is how the current is generated, current is produced. Now let us think of an electromagnet. See, whenever current is passing in the coil, okay, this is we have a source here, so we are supplying energy to this coil. There is current in the coil. So what happens here? This is a direct current. You can understand because the motion of the electrons, you can see it's all in the same direction. Okay, this is a direct current because we have a battery, DC battery here. But what I can perhaps show you is that I can change the polarity. Okay, so the motion of the electrons, you can see traveling in the opposite direction. I can change the polarity of that in both the cases. But you should understand that there is no change in the field around it because it's a direct current. Okay, constantly you can see the magnetic field. But now we can do a small experiment here. Instead of this DC battery, suppose I connect it to an AC source. Okay, where I can also think of changing the frequency of the AC current. You can find that there is a change in the magnetic field very consistently taking place in both directions because you can see the electrons moving in one way and quickly in the opposite way. Because this change takes place so rapidly because the frequency is about 50. So 50 times in a second, the direction is changing. Okay, so there is an EMF here in the circuit. It's connected to the AC source. You can find the change in the magnetic field. Okay, and very quickly the change is taking place. This is how we understand that there is a magnetic field produced when current is passing in the conductor. Because this is a coil here, current is passing there, we have a source here, we can find there is a magnetic field produced around that. Now we can think of how a generator works. See, you must have noticed that when you go to places where you have say a dam, water is stored in that, and that's the energy stored, that's a potential energy, gravitational potential energy. When water falls from such heights, and you can find the turbines rotating like. So here I show you how a magnet is rotating and which eventually produces current and which can be stored so that the current can be supplied, the energy can be supplied to our houses, industries or whatsoever. So now I am trying to show you that when this magnet is rotating with, you can also see the rotations per minute, about 56 here. So see it rotates and produces EMF. So here you can find the electrons moving in two different directions. Very quickly it is changing because this generator is an AC generator. Okay, so this is how you should understand. Here let us observe that there is a conductor. That conductor is a straight conductor, and what you see here is that the small drops like electrons are represented here, and electrons are moving downwards. That's what you observe actually, like electrons are moving downwards, and it's only just a representation is given. But you should understand that the direction of conventional current is exactly opposite to that of flow of electrons. So you should think of this: electrons move from negative to positive, but we say that current is moving from positive to negative, because that's the conventional direction of current actually. So electrons are moving downwards here. You can see the representation of electrons, but the current is said to be moving from positive to negative. And what I want you to observe here is that there is a magnetic field produced around the coil. So you can take a compass and you can see the motion of that needle, magnetic needle, and when I move it around, usually what happens, what you should study here is, you see the direction of that compass, it's changing continuously. So that's a magnetic field, and that's the direction of the magnetic field is represented when I'm moving this coil. But you also should understand, probably in higher classes, as I move this needle away, the strength of the magnetic field gets reduced. The magnetic field is very strong when I am close to the conductor, and as I move away from the conductor, the strength of the magnetic field is not so much. It is insignificant, though not inconsequential. So what you should understand here is, this magnetic field produced when current is passing in a conductor can be explained using your Amperes right hand rule. So when I say right, you must take only right hand. Let us say the current is moving upwards. That's indicated by my thumb. My thumb indicates the direction of current in the upward direction. Now the other four fingers, the way they are curled, and they indicate the direction of the magnetic field. Now you should understand, current is moving upwards, and when you see from the top, you can see that the magnetic lines of force, the magnetic field, you can see it is in the counterclockwise direction here. What you can also understand is, when I put the thumb downwards, if that is the direction of current, I can show it here. When this is the direction of current going downwards, you see these magnetic lines of force, they are moving in the clockwise direction. You always have to use only right hand for this. This is Amperes right hand rule. When the current is moving upwards, when you see from the top, you can understand that the way the fingers are curled is counterclockwise direction. And when the current is moving downwards, you can find that these fingers, they curl up in the direction of the clockwise direction. So magnetic field is developed around a straight current carrying conductor. Okay, you can also notice the direction of the magnetic field. So you should understand, this is the first point actually. Now I am talking about an electric motor. This electric motor works based on the principle of Fleming's left hand rule. Okay, you're all familiar with this now, that there is an external magnetic field in a motor. External magnetic field, this you can see the north pole indicated in the red color, and you can see this in this green color, you have the south pole. So magnetic field lines, I want to show only magnetic field lines here, just watch, and that's the direction of magnetic field. You can see these blue colored lines from this north pole to the south pole. So field is always indicated with this forefinger, it's downwards here now. That's what we notice. Now I want to show you, look at the coil now. So in which the current is passing, because this is connected to the source. You also can identify the poles here, positive terminal and the negative terminal. So now watch this coil very carefully, that gives you the direction of electric current. So I want you to be very keen here that there is a change in the direction of current when it passes the slip rings here. Okay, so you have the carbon brushes here and the circuit is broken at some instances, and when the current is resumed once again, and what you find is the current is flowing in the opposite direction. Watch this red colored arrow carefully. It is towards me, a little later it is away from me, and that's what you should understand. The current is disrupted for a while and the direction also changed. So if you watch the coil very carefully, you understand the direction of current. The direction of current you can remember in two ways, like it can be even towards me or it is away from me. So my forefinger is indicating the magnetic field. It is downwards. Okay, that you cannot change. The current is away from me or current is towards me. Those are the two cases that arise. And now you should understand, because the current is passing in the coil and that coil is placed in the external magnetic field, there is a force acting on the coil. So that force is indicated by the black arrows. Now you can see only the force acting on that. Why is the coil rotating now? Where is the need for it to rotate? Because there is a force acting on them. Because a coil is placed in the magnetic field which eventually rotates because there is a force acting on the coil. So you can see now all the three directions: direction of current, red colored arrows you can see, magnetic field, that's a blue colored arrows you can see here, and now you can see the black arrows which indicate the motion of that coil. So when this coil is rotating, and what you should understand is that it's a motor is working. Okay, so the motor works this way. Like, I just want to repeat that how this should be connected to the Fleming's left hand rule. Magnetic field is acting downwards. You see only my left hand downwards. My central finger talks about the direction of current. Now it is towards me, and my thumb indicates the motion. That's the force acting on the coil. Now, in the same way, when I keep the I don't want to change this field direction. It's exactly the same. When current is away from me, the motion, you can see that these three fingers are stretched perpendicular to each other, and now you can understand the direction of force acting on the coil. So what I can do now is I can change the direction of this motion. Number one, I can stop it for a while and I can resume that, and I can show you when the current is disrupted. Now you see there is no current flowing, and again when I just say resume, the current continues to flow now. So when the motor is working, what's happening here is the current is disrupted for a while, for an instance, and it resumes very quickly. So due to inertia of motion, it continues to move. Okay, so you can just set everything, and you can make it move. And here what you need to do is that I can increase the frequency. I can make this motor move a little faster. Okay, so when this motor is working, so you should understand that this can be used maybe in your fan, or maybe you can use your kitchen devices like your mixer grinders and all that. So you have a motor there which works, which makes the coil move. Children, now we are talking about a few ideas in light. You're all aware that light travels, it can travel in vacuum also in the form of electromagnetic radiation. And unlike sound waves, which are mechanical waves, light does not require a medium to travel. You can understand that we are all on the earth, on the surface, and sun is at a distance of 150 million kilometers. Despite that fact that light can reach earth, like very, very fast it travels and all that, it can travel through vacuum, and with a reasonably big speed, about 3 lakh kilometers per second. So what I want to show now is that you can understand that light, you have two theories which justify this propagation of light: particle theory and wave theory. And let me say that now this is my source of light. Okay, so there is a change in the medium. You can understand this is a rarer medium, air, and you have water here. This is a denser medium. And how do you understand that this is a rarer medium? The refractive index here is 1 for air and 1.33 for this water. So naturally you understand that this air is a rarer medium and water is a denser medium. Now you should understand that if there is no change in the medium, assume for some time that you have air here also. There is no change in the direction of light, because here you have air and here also you have air. There is no change in the medium, and therefore the light ray has just gone straight. Okay, but now we are not interested in this case. We are interested what happens when there is a change in the medium. So you have water here. So what you should understand here is that when the ray, a light ray, is coming from the rarer medium to the denser medium, instead of going straight, there is a bending here. And that bending you should understand, this dotted line is this normal. This light ray has bent towards the normal, because this is rarer medium, this is a denser medium. So how do you understand this actually? The angle between this normal and the incident ray here, that we call angle of incidence. Let me get my protractor and start measuring that actually. So you can understand that the angle you find there is somewhere around, say this is 30, this is 40, and you are at somewhere around 45. So angle of incidence is 45 degrees. When you observe this angle of refraction, it is less than that. Okay, so it is almost 30 degrees. So what you should understand is that when the ray is going from rarer medium to denser medium, the light ray is bending towards the normal and thus making this angle of refraction less than the angle of incidence actually. So I can also move this for different angles. I can show you how it works. There is a small point I want to tell you. You cannot consider exclusive refraction. There is a little amount of light which is getting back into the same medium. So reflection completely cannot be ignored, So for the time being you watch refraction, but also think that there is a little amount of reflection where the light bounces into the same medium. So I can vary the angle of incidence. In all the cases you notice something, that the angle of incidence is larger than the angle of refraction, because the light is traveling from rarer medium to denser medium. So let me now make this denser medium and this rarer medium. So it's to say that I have water on the top, whereas air beneath that. So when you have air, and this is an interesting case actually. The angle of incidence here, is more than the critical angle. Okay, when the angle of incidence is more than the critical angle, the ray does not enter the rarer medium, it goes back into the same medium. That is called total internal reflection. This case let us ignore for the time being. I want to decrease that angle of incidence. Then you find the refraction is taking place. So this is incident ray and this is refracted ray actually. Okay, so what is that you should notice here is, if you observe the angle of incidence, this is about, say, the same angle which we measured earlier, about 40 degrees there, and here the angle of refraction is reasonably large. This is 30, 40, 50, 55 degrees. So angle of refraction is much larger than this angle of incidence. This has happened because the ray is starting from the denser medium going towards the rarer medium. In that case what happens, the bending is away from the normal. When the light ray enters from the denser medium to the rarer medium, the angle of refraction is larger than the angle of incidence. And there is an interesting observation here that you can see. Imagine for some time you have a wave. Instead of thinking that light travels in a straight line, the rectilinear propagation like a particle and all that, I can think of a wave. So when you see the wave, what you understand here is that So it behaves exactly same way as the particle, but you also can notice a change in that because the velocity is changing. When the velocity of the light is changing, that you have to notice here, like. Okay, so this is how we understand the refraction, okay, light ray traveling from one medium to another medium. Now let me tell you what happens. This is another case we are studying. I take a prism. I want that incident light to pass through the prism. So usually what you can observe is that there are two refractions taking place. When light enters from air into glass, and when from the glass it comes out, we call it an emergent ray. So let me take, say, a prism. So this is my prism and this is my source of light, and I can change the position of that. This is a typical case what I am interested to study actually, like. So this is the incident ray entering into this prism, and it has come out, and you can say this is the emergent ray. So incident ray, refracted ray and emergent ray. You also have a little facility to change here, like, yeah, you can do that. So when you find out the refractive index, what you notice here is that you just let this incident ray produced actually. Okay, on paper you can do that. You produce the incident ray and you also produce the emergent ray. We are going to do an experiment for that, and the angle between these two, incident ray produced and the emergent ray produced backwards, that gives you the angle of deviation. It was supposed to go that way. Because of this prism, it just came out like this. So you know that that's the angle of deviation. You see, it's interesting to note here that what happens if I change the wavelength here. So you can think of changing the wavelength. You know that it's about 4000 angstrom units to 7000 angstrom units, or you can say when you measure in nanometers, it's about, say, 400 to 700. So I want to change the wavelength, and that is going to change the color of the light. Okay, so what you should understand is when you take red, the wavelength is more. When the wavelength is more, the frequency is less. You have studied Planck's law that when the frequency is less, the energy it is associated with is less. So E is equal to h nu. Okay, when nu is less, E is less. So you should notice here that when I take, say, red colored light here, the energy is very, very less because the frequency is less. Frequency is less. How do we know that? Because the wavelength is maximum 700 nanometers. When you reduce the wavelength as the color changes, and finally you see that it is only about 400. When you find this 400 nanometers, and what you should notice that that's the like violet color, like. So you have the spectrum. Now I am interested to show you, because dispersion is a wonderful phenomenon, like you all like it. So what I do is that I just reverse the colors here, and I can show you that here you can find out the various colors which are produced here. So I want you to observe one thing very specifically, like when you see this dispersion, you should understand that there is a light, okay, it's a monochromatic light, a single colored light passing through this prism, and the bending of various colors is not same, because different colors, they bend differently because the wavelength is different. And when you observe these colors, you cannot think of getting all the 7 colors distinctly, because it's not possible for you to get 7 different colors. The reason is very simple, because however narrow you think of this light ray, it's not, say, one single ray going and giving you the 7 colors. In fact, it is a beam. Even if you say it's a narrow beam, it's a beam. I think like, see, when this is a beam, what happens? The rays which come out of that, emerge out of this prism, they overlap, and you don't find all the colors. So that spectrum is generally, it's an impure spectrum. You can't think of having a pure spectrum where you can observe all the 7 colors very distinctly and all that, because it's very difficult to make that arrangement. You need a spectrometer, you need a good prism, and you have to have a narrow beam, you have to think of having monochromatic light. So all the necessary conditions would make it possible for you. Maximum you can see, say, 1 or 2 more colors. It's definitely not 7. Okay, so this is what we mean by the dispersion of light. Okay, when a light is traveling, passing through the prism, and all the white color gets split into different colors, and you call that a spectrum. Okay, the same way you also can talk about the scattering of light, because like light enters the Earth's atmosphere. You all know that the Earth's atmosphere is composed of so many material particles, like you have nitrogen, oxygen, carbon dioxide, water vapor, and all that. And when light falls on these material particles, like the light gets scattered. And you also understand that blue color scatters more. So the light which is scattered by these material particles as the light enters into the atmosphere makes the sky blue. Okay, so that's how you need to explain that why is the sky is blue in color and all that. Similarly, it is easy to understand why we get a rainbow and all that, like. Okay, this is an interesting experiment, and we are taking glass with which a prism is manufactured, and we need to determine the refractive index of this prism. Okay, so how we do this practically is that we keep the prism on the paper, and we trace the base of that prism, and we place two nails here. Okay, assuming that those two nails indicate the direction of the incident light. We place two more nails here on the emergent ray, you can understand here, and when you watch from here, those four nails, they appear to be in a line. Strictly speaking, they are not in a line, but they appear to be, because the light is bending here twice when it is entering from this air into glass, and from glass into air, it is bending twice, eventually giving you a feeling that the light is in a straight line. And therefore you find two pins on the incident ray and two pins on the emergent ray, they appear to be in a line. So now we have drawn a normal here at the point of incidence where the light has fallen on the surface of the prism. We measure this one, it's indicated in red color, that's the angle of incidence. So you also can understand that this incident ray produced and emergent ray produced backwards, and that gives you angle of deviation. If you are not able to watch it, probably what I can do is that I can increase the angle of incidence and I can show you that angle of deviation. See, I think it's more easy for you to notice this angle of deviation. Incident ray produced and the emergent ray produced backwards. This is the angle of incidence, angle of deviation. So when you need to find out the refractive index of the material with which this prism is made, you have a formula, mu is equal to sine of a plus d by 2 over sine of a by 2. A is the angle of the prism, which you can determine very easily, but what we need to get here is angle of deviation. So angle of deviation is changing as you change the angle of incidence. So I have here a graph where I have taken angle of incidence on the x-axis and angle of deviation on the y-axis. What happens here is, as I increase the angle of incidence, initially there is a decrease in the angle of deviation, but if I further increase that angle of incidence, the angle of deviation again increases. I repeat my point, as I increase the angle of incidence, angle of deviation decreases, and as I further increase the angle of incidence, the angle of deviation again increases. You watch this very, very carefully. First, the angle of incidence is less and angle of deviation is, it's very high. Now, as I increase the angle of incidence, you should notice that angle of deviation is decreasing. It reached the bare minimum, and this is called angle of minimum deviation. But if I further increase the angle of incidence, you find that angle of deviation is increasing. At one point, you should notice that the angle of deviation has reached the bare minimum. Okay, and that is essential. You should have noticed when the angle of incidence is about 50 degrees, the angle of deviation is just 37.2 degrees. So that is where you need to take this reading very, very carefully. So what we do is we take I on the x-axis, okay, it's a measure of angle of incidence, and we take angle of deviation on the y-axis, and we draw we get a parabola Okay, this is the relation between I and D, and from the graph you need to find out the angle of minimum deviation. Okay, so that's what you have here, 37.2. So you just see that how it is changing. Okay, and it has come down, it's a bare minimum, okay, 37.2, and then it is moving up actually, like it's increasing. So once you notice this angle of deviation, you also know the angle of the prism, the A. You can substitute these two in the formula, and that's how you can determine the refractive index of the glass with which this prism is made. Okay, we're going to talk about the lens and the mirrors. Like here you have the example of a convex lens. It's a bifocal lens actually. And if you think that this surface, one side, is taken from, is cut from a sphere, and that sphere has a center, and that's where we have this center of curvature. So this surface has the center of curvature here, and the other surface, which is a convex surface, has the center of curvature this side. So you can find C on either side. Okay, that's the center of curvature. The distance between the center of the lens and the center of curvature, and this distance is the radius of curvature. Okay, this is the radius of curvature, distance between the center and the center of the lens actually. And somewhere midway through you have the focus. So how do you understand what this focus is all about? When you have rays coming from a very, very distant place, coming parallel, they've come parallel to the principal axis here. After refraction, they all converge at one point. Okay, and that point is called principal focus. Let me repeat this point. Rays coming parallel to the principal axis, or rays coming from a very, very distant place. After refraction, after they pass through this this lens, they converge at one point, and that point is the focus. So you have focus this side, you have a focus this side as well. Now let us discuss the different positions of the object and how the image is formed. I want to get my object very close to the lens. It's something like less than the focal length. You can see this is the center of the lens, and this is the focus, and object is within the focal length, less than the focal length, very close to the lens. And what you find is the image is formed on the same side. I observe from here, this side. Okay, the image is formed on the same side, and you also can easily observe that it is a magnified image, it is a virtual image, it's an erect image. Whenever you write an image is say virtual, and you can write it's erect, because all real images are inverted. Okay, so now slowly I want to move away from the lens. Now my object is at, let's say, F. When I keep the object at, see, the focus, I don't know where all these parallel lines are going, and where they meet and all that, like so that happens at infinity, because they're all going parallel actually. So when the object is at focus, the image is formed at infinity. We can't talk about the properties of the image, because the image is formed very, very far at infinity. But now there is a case where the object is between F and C, because this is the focus and this is the center of curvature. Between F and C, when you place the object, you see the image is formed on the other side. Okay, and this is an inverted image, it's a real image. And also you must have noticed, compared to the height of this object, height of this image is more, which tells you that it's a magnified image. So now let us talk about the properties. It is real, it's inverted, it's magnified. Let me take you to the next case where I keep the object at C. When I keep it at C, and what you notice is that the other side also it is at C. This is at C and this is also at C, and there is no change in the size, but only thing is it is inverted because it's a real image. And if you want to talk about the properties of that, you can say that it's real, inverted, and it's the same size. But the last case, you see, when I keep this object away beyond C, and you should have noticed the image here is between F and C, and notice that the size of the object is more, but the size of the image is less. So image is a diminished image because the size is reduced. So when the object is kept beyond C, what you notice is that the size of the object is less, and it's a real image, it's an inverted image. This is how we understand see the position of object at different locations, and what happens to the image, different characteristics of the image you study. But now what I do is, from lens I can straight away go to a mirror. Okay, so this is a concave mirror, and the principle here is not refraction, this is about reflection. So the first case what I do is, I keep the object very close to the mirror. Okay, so the distance between the object and the mirror, okay, pole of the mirror, this is less than the focal length. But here you see the image is formed the other side, it's a virtual image, it's a magnified image, and this property helps you to use concave mirror as a shaving mirror. Okay, so the mirror is very close to your chin, and you can see your chin much larger, and therefore you can have a close shave. Okay, that's how it works actually. So now I take the object, I keep the object at, let us say, f focus. I can't understand the properties of this because all these rays are going parallel and the image is formed at infinity. Okay, that case we can leave. But when the object is moved between f and c, and what you notice is that the image is formed beyond c. Okay, it's a magnified image, real image, okay, inverted image, and because the object is between f and c, but the image is beyond c. And the next case is that I bring the object to c, and what you notice that the image also is at c, but here you find the same size. Okay, real, inverted, same size. But notice that as the object is moving away, the image is getting closer to the mirror. But here, compared to the size of the object, the size of the image is less. So it's a diminished image formed between f and c. And you can also imagine it is taken very, very far, okay, to infinity, and this image shifts to focus actually. Okay, so this is how you understand the working of a mirror. But there are two other cases, of course. I should show you a concave lens, and this concave lens, it's easy to understand because wherever you keep the object, the image is formed on the same side, it's a erect image, it's a virtual image. There are no different cases here, it's only one and the same case. Okay, so this is concave lens. Exactly in the same way, you have a convex mirror. Okay, this convex mirror, you should understand that the same case, because there is no change in that, always the image is diminished and all that. So let us understand this particular convex mirror. This convex mirror is used as a rear view mirror. Okay, when you are in the driving seat, when you keep the mirror, of course, by your side, you see the objects coming from behind. Okay, suppose there is a truck coming, you can't afford to have an ordinary mirror, plain mirror, because you can't see the complete truck. But in case you have a convex mirror, the size of the truck is reasonably reduced and you have the view of the complete road in your small mirror. Also, you must have noticed that on the mirror, okay, it is written that the objects which appear in the mirror, they appear to be closer. So the truck appears to be closer, but actually the real distance is more. So you should have an estimation of that when you use the driver's mirror, okay, the convex mirror placed near the driver, he can see behind the vehicle that's coming, and he can think of giving the way to them, or he can overtaking or whatever it is, and that's how the rear view mirror works. But the advantage here is he can see the complete road in the small mirror. Okay, even when he is taking the vehicle in the reverse direction, so that's very useful, of course, that rear view mirror. Also, when he when a vehicle coming from behind, of course, okay, whether from left side or right side or whatever it is, he can accordingly understand how he has to change his driving or whatsoever. Okay.